Let's go back and compare something like this again. Suppose I want to know, so this part should be review, if I want to know the solution to this kind of equation, this is pretty easy. I can take the square root of both sides. Now, as a small caveat here, this does not equal x, but rather it equals the absolute value of x. And that's because we don't know whether x was positive or negative before we square it. So we'll get square root of 5 equals absolute value of x, or plus or minus 5 equals x. So the square root undoes x to the squared. It undoes this power. Not being entirely rigorous here, so if you're intending on being a math major, we should be more clear here. The square root is not the inverse of x squared, it's just the inverse of x squared if x is restricted to positive or non-negative numbers. So, okay. Well, what if I want to solve this equation? I can't take the square root. I mean, I can, it just doesn't do anything. So if I do this, the square root only undoes the square, because that's what the square root is. By definition, the square root of a square gives you the number you squared. But here, I'm not raising to the power of 2, I'm raising to x, and x can be anything. So I would need every possible root. That's not going to work. So, what undoes 2 to the x? Well, going back over here for a second, what if I'd had 5 equals x cubed? I couldn't use the square root here either. I would use a different root. I'd use the cube root. And if I had x to the 4th, I would be another plus or minus the 4th root of 5. So for each power, I have another root. Well, the situation is similar over here. For each base, I have a different function to undo it. And it's just like over here. For each power, I have a different root to take. Square root, cube root, etc. So the function that does this is the logarithm. All right. So here's what it looks like. Going back to our initial equation, we have 5 equals 2 to the x. I would take the log. The log what? Well, the log base 2. I need the log that undoes that. I take the log of both sides. And then I have log base 2 of 5, whatever that is, equals log base 2 of 2 to the x. Now, just like the square root of x undoes the square and the cube root of x undoes the cube, so does the log base 2 undo 2 to the x. So this ends up being just x. Now, that doesn't really tell you what this thing is. And logarithms didn't actually come about for this reason. They came about because of calculations. When Napier, the inventor or discoverer of logarithms, created logarithms, it was because sailors were doing complicated spherical trigonometry calculations at sea, making a lot of mistakes. Logarithms, as I'll show you in a little bit, have a whole bunch of nice properties that make calculations easier. He made a whole book of logs of sine, logs of tangent, logs of trig functions to make seagoing calculations and also astronomical calculations a lot easier. This is somewhere around, I think, the 16th century. And this is long before anything like a calculator. So this is where you're going to see them, in the sense that you're using them to solve equations. And so they're a function all by themselves. You can have, f of x is log base 2 of x, or you could have another function, log base pi if you wanted to of x, and etc. And you can do derivatives of these things. They're f primes, and you can do integrals of logs, and so on and so forth. So their origins is in calculation and navigation. The algebra of them, part of it is solving equations. They're a function in their own right, and they have interesting applications in science, so you can do calculus on them. Let's look at some algebraic properties. If you want me to prove these, I can, but the important properties are as follows. The log, any base, of a product, if you have a big X and a Y, you can break this up. And this should look vaguely familiar if you think about how, if you were to take, say, like 2 to the x times 2 to the y, it's 2 to the x plus y, right? Multiplying the functions adds the exponents. This is sort of the opposite. If you multiply the exponents, it's adding the logs. It's related. Maybe move the camera a little bit. Another property is log a of x divided by y. And that would be log x minus log y. So logarithms are taking things down a notch. Multiplication is addition. Division is subtraction. And one more. If you had x to some power, the power comes out front. Now this one actually follows from the first, right? If you had a log of x plus x, or sorry, x times x, that would be log of x plus log of x. So if you have log of x, actually, let's just show you. So let's try to understand a couple of these. So if I had log of, say, x to the fourth, that's log of x squared plus log of x squared, which is log of x plus log of x plus log of x plus log of x, which is 4 log of x. And it's actually the same for division. If you have x divided by y, that's log of x times y to the minus 1, which is log of x plus log of y to the minus 1, which is log of x plus a minus log of y. So the most important thing is this this business here, that products go to sums. And historically, this is the reason why math classes run you through these things. Historically, this was crucial. Imagine if you had to calculate something like the 4th root of 365 times 12.6 divided by 17.01. Now imagine with no calculator, and imagine you're doing this because you're building something like the Hoover Dam. The Hoover Dam was built before calculators. So this was pencil and paper stuff. How do you do this? All right. Well, you take the logarithm. Now this isn't so important anymore because we have calculators, but the algebraic properties are still used in other applications. So if you do this, the 4th root is a 1/4 power. Just going to run through this so you can kind of get a little history out of it. All right. Now this is division. So I have a 1/4. Then I have a difference of logs. Whoops. Times 12.6 minus log of 17.101. Product. And any of these things, if you want to see more steps, just let me know and I can flesh this out. And then what you'd have are tables of logarithms. And you can just look these things up. Look up. And it might seem like you'd have to have a set of logarithm tables for every conceivable number, but you don't. Because you can write this as log of 3.65 times 10 squared, scientific notation. Log of 1.26 times 10 minus log of 1.701 times 10. So when it's all said and done, what do we have here? Well, we'd have log of 3.65 plus log of 10 squared plus log of 1.26 plus log of 10 minus log of 1.701 minus log of 10. Those cancel. This is equal to 2. And then all you'd have to look up in your log table, if this were like the 40s or something, would be these numbers. You just need a log table that goes up to 10. And you can look up all these things. So you could even actually turn this one into a number less than 1. Right? This is 0.365 times 10 to the minus 1. Actually, times 10 to the plus 1. So you can pull out another 10. So the properties of logarithms allowed you to have a table of values, a small book, that you could do calculations like this. You can just look up these numbers, and you can add them longhand, and then multiply by 2.5 or divide by 4. All these things can be done. Calculations like this were done this way, less than 100 years ago, to design things like the Hoover Dam. And if you've seen slide rules were designed on logarithms. So there's a little bit of perspective on the logarithm.